Welcome to Korea. So thank you for giving those contributed talks. And I will really appreciate them for 5 days. So this is the last contributed talk today, so I want to be very light, but I'm not really sure. But it's good that there are a couple of talks on Schubert calculus, so people know about the definition of flag varieties, and also the Schubert varieties and Schubert classes, like basic properties of the setup for the Schubert calculus. So I'm going to be very brief about those introductions. So let me do this. So, by the way, I'm talking about type C Schubert calculus. So type C Schubert calculus, you're looking at a symplectic group. So you look at symplectic vector space and then automorphism of that. It's symplectic group. And that's type C classified as Dinkin diagram. And then, so my talk is about some formula to express Schubert classes in terms of some ring generators. But I want to discuss those geometric classes at the level of some polynomial representatives, right? So that's my goal on this picture, double Schubert polynomials. Those are the polynomial representatives for the equivariant Schubert classes. So Fn to be a flag variety. So those are complete isotropic flags in the symplectic vector space, C to the 2n. You can just put a standard symplectic structure there. And then the Y group is very important in Schubert calculus because it indexes these Schubert varieties. And the Y group in this case they are signed permutations. It's a permutations on those 2n letters. So 1 and 1 bar. 1 bar you can think of it as -1, the 2n minus 2, 3n minus 2, and then minus n. Yeah? And then not just permutations of these letters, but they have to be generated by it's a composition of those SL, S0, S1, S2, S2, so those transpositions. Yeah? So I'm not talking about all permutations of these 2n letters, but it has some properties. Yeah? And then if you look at the example, it's clear. So 3 bar, 2 bar, 1 bar, 1, 2, 3. It goes to, for example, 1 bar, 3, 2 bar, 2, 3 bar, 1. So it's sort of anti-symmetric, yeah, from the middle. Right? So 1 goes to 2, then -1 has to go to -2. Yeah? So these are called signed permutations. Okay? And those permutations, those particular permutations of those 2 name letters are generated by those transpositions S0, S1, S2, S3. Okay? So this is the Y group for the full flag variety, the symplectic group. Okay? And then Schubert classes are indexed by the elements of this Y group, and it becomes the basis of a cohomology ring. Yeah? And then now I'm talking about equivariant cohomology ring. So when I say it's a basis over a polynomial ring with n variables. Yeah? So it's the basic thing about equivariant cohomology. And the question is, a very basic question, right? So you're looking at the cohomology ring, but then usually cohomology ring is, you can write it as a quotient of polynomial ring. Yeah? So if you can sort of identify a honest polynomial ring with this equivariant cohomology or cohomology ring, it's better because when you look at the quotient ring, you're dividing by ideal. And this ideal, the computation, it makes computation very difficult. Like if you want to do in a computer, the ideal is the big problem in the commutative algebra people. Right? So if you can think of this equivariant cohomology as an honest polynomial ring, it's a big progress if you want to understand the ring structure with respect to this basis element. Yeah? So here is the answer to that question: can we represent the cohomology as a polynomial ring? Here is the result by Ikeda Naosu Mihauchi in 2011. So as I said, equivariant cohomology ring is already a quotient of polynomial ring. So as it is, it is not going to be a polynomial ring. Right? So it's a finite rank free module over polynomial ring. So it's not going to be a polynomial ring, but there is a natural inclusion of Fn to Fn plus 1. Right? So like n by n matrix, you can embed it as n plus 1 times n plus 1 matrix. Yeah? So that inclusion makes a sequence of flag varieties. Yeah? And then you can just take a cohomology of them, and then there's a pullback maps, right? The sequence of pullback maps. And then you take the limit. Okay? That is this ring. Yeah? So basically, you're looking at a sequence of quotient polynomial ring, but then you are taking the limit of that. Yeah? And then that object is isomorphic to a sort of honest polynomial ring. Yeah? And then one thing you have to be careful is we are working in type C, and in type A, you don't have this Q1, Q2, which is very particular in type C. And if you get rid of this Q1 and Q2, it's just an honest polynomial ring generated by infinitely many variables. Yeah? But in type C case, these Q1, Q2 are certain symmetric functions in terms of some x parameters. And then these Q1, Q2, Q3, they are defined by this generating function. Yeah? And because it's using infinite number of variables in this generating function, this is not a symmetric polynomial, but symmetric functions. Yeah? Right. But it's good. You have so if I become honest, this is a subring of a polynomial ring. Yeah? But then among those QIs, there's some relation. Yeah? So it's a subring of z of x1, x2, x3. Just disregard t and z. Okay? So when you look at this theorem, yeah? Also the content of this theorem is there is a Schubert class, right? Defined by the so indexed by Y group elements. Yeah? And then there is a corresponding polynomial. Yeah? And then this isomorphism, so this correspondence becomes a ring isomorphism, so that if you want to calculate the structure constant with respect to these Schubert classes, you can just calculate the structure constant with respect to those polynomials, honest polynomials. Okay? And so now it becomes a purely algebraic problem of computing the structure constants with respect to those Schubert classes. Oh. Right. So ultimate goal is we want to find the structure constant with respect to those double Schubert polynomials indexed by W and indexed by Y group elements. Okay. And I'm also taking this limit of Y group, right? The Wn is it's a part of permutations on 2n letters, but then you can just embed this thing into Wn plus 1. So the permutations of 2n plus 2 letters. Yeah? So in that way, you have a limit of that group. In this case, you can just take the union of those Wn's. Yeah? All right. So ultimate goal is to find the structure constants of those double Schubert polynomials. But the strategy is you want to find a good expression of this Schubert class or double Schubert polynomials. Yeah? And in the previous talks, he was talking about type A, and then this double Schubert polynomial was given in terms of pipe dreams. And it's sort of combinatorially closed formula, right? But algebraically, so it's written in terms of combinatorial objects, but when you say closed formula, you want to write it as in terms of some elements, but then in some algebraic operation makes the polynomial. Right? And in that sense, the closed formulas for part of those double Schubert polynomials are known. Right? So not all those double Schubert polynomials have a closed formula yet. It hasn't been found yet. And an example is, so now we are talking about full flag varieties, but then the part of this cohomology ring, there is a subring given by Grassmannians. So full flag, your sequence of subspaces, but then the Grassmannian is just a single one. Yeah? And it's a part of the cohomology of Grassmannian is a subring of the cohomology of full flag. So basically, when you are working on the Grassmannian, you're looking at some part of those double Schubert polynomials. That part I will be explaining in a moment. So the double Schubert polynomial corresponding to Grassmannians, there have been very nice closed formulas in terms of determinant of Pfaffians. So in this type C, this Pfaffian operation is very important, and it started by Schur, and Prague has realized so this gives you this Pfaffian gives you the Schubert class for Lagrangian Grassmannian, and then some generalization of that formula worked out by all those sequence of people. Yeah? And I think in the cohomology theory, my work that I'm presenting right now is the last one for the Grassmannian. Yeah? Equivariant Giambelli formula for isotropic Grassmannian is the last formula for Grassmannian case. So now you can talk about K-theory or copordism or whatever. So there are more generalization, but in the cohomology theory, the formula I'm presenting is the absolute formula. Okay, so to talk about the double Schubert polynomial corresponding to isotropic, the Grassmannian part of the full flat variety, I have to mention a particular kind of signed permutations. Okay, and then some combinatorial objects that indexes those particular permutations. So I have to go through this. Right. So I mentioned signed permutation, right? There is, so if you look at this 2n letters, 1 minus 1, 2 minus 2, and then if it goes to these elements, you don't need to look at the image of negative numbers, the bar numbers, because it's a signed permutation. It's sort of anti-symmetric. So if you know the target of 1, 2, 3, the positive numbers, you know where the negative numbers go. So you can just pick up W1, W2, W3, those positive, the image of the positive numbers, and that's called one-line notation. Yeah, it's just a simple notation to write the signed permutation. So among W1, W2, Wn, there might be some negative numbers or bar numbers. Okay. Right. So here's example. So, example is right there. Yeah. So this 2, 4, 5 bar, 1 bar, 3. This is the one-line notation for certain permutation. Yeah. So among permutations, I have to define this k-Grassmannian elements. Yeah. And so the permutation is called k-Grassmannian elements. If it's one-line notation, it's in this way. So first k letters, it's a positive number increasing. Yeah? And after k numbers, there are a couple of negative numbers, and it's also increasing. And then after that, there are some positive numbers, it's also increasing. So among those elements, the letters in this one-line notations, there are these inequalities. Yeah? So if you know type A Schubert calculus and the Schubert calculus for the Grassmannian, you often hear about this Grassmannian permutation. Right? So you have a permutation of n letters, and the Grassmannian element means that up to some point there's only one descent. So one descent, until then the number is increasing, but then after that it drops some part, but then it started to increase again. So there's only one descent, that's the Grassmannian element for type A. And this k-Grassmannian element is a type C analog of this Grassmannian permutation. Yeah? And then for convenience, we introduced this characteristic index. It's just we need it to write the good formula. Yeah? So it's kind of a little technical thing, but these numbers significantly simplified our computation. Yeah? So it's very useful, but not sure the geometric meaning of this. Combinatorially, this index was very useful to describe things. So it just takes the negative part, right? Zeta 1 through zeta s, and then you just subtract 1, and that's the first s letters. And other part, you pick up those v1 through vn minus k minus s, and then just put minus. Yeah? So this just came up in the computation. So like the example is here. So this is two Grassmannian permutation. Yeah? So 2, 4 increasing, and minus 5, minus 1 increasing, and then 3. Yeah? So there's only one descent. Yeah? Descent is this indicated by this bar. Yeah? Okay, and then for this, the characteristic index is you have 5, 1, these negative numbers. Yeah? So you have 4 and 0. And then you have, oh wait, what is this minus 1? Yeah, I think this minus 1 shouldn't be there. Sorry. So 4, 0, minus 3. This minus 1 is typo. It's not there. Yeah? Okay. So you collect all the k-Grassmannian permutation with this definition, W infinity k. I don't specify the length n when you write this W infinity. So you can imagine you have 6, 7, 8, 9, 10 after this 3. Yeah? So it doesn't change numbers after 5. So that way you can identify it with the permutation on the infinitely many letters. Yeah. Okay, and then there's some combinatorial objects, right? Lambda, it's a permutation, the partition, yeah? Lambda 1, the decreasing sequence, and it's called k-strict if it satisfies this condition. So if lambda I is greater than k, and everything before that becomes strict partition. Strict partition means that this inequality becomes a strict decreasing. Yeah? So for example, lambda 6, 5, 3, 2, 2 is too strict. Yeah? So if the number is greater than 2, 3, 5, 6, this is strict, but less than 2 or equal to 2, it's not strictly decreasing. Okay? Okay, and then you write pk, the set of all k-strict partitions, and this k-Grassmannian permutation and k-strict partition, they are in bijective correspondence. Yeah? So in this way, so when you look at the full flag, you have to look at each Schubert varieties are indexed by permutation. But if you go down to a Grassmannian, then often the Schubert varieties are indexed by some combinatorial object like partition. Yeah? And then the number of partition gives you the degree of the class. And that's the nice thing about those partitions. Okay? And then this correspondence, I just draw a picture of that. It's not too difficult. So 2, 3, 5, 1, 4, and 5 and 1 are negative, right? And then, so how do you get the partition out of this permutation? And this is it's written in Lucrèce Tambakis' paper on the Giambelli formula for the non-equivariant isotropic Grassmannian. So you have to read that paper to understand this, but if I just tell you, it's not too difficult. Right? But reading this from the paper is difficult. So you look at these negative numbers, 5, 1, and you make a black boxes, 5 boxes and 1 box. And then you have 2, 3, and 4 positive numbers. Yeah? So 2, 3, these two letters in the beginning is indexed by red dot, and then 4 is blue dot, right? And then if you look at this 5 by 5 square, and this upper half, yeah, it can be filled by black boxes and red dot and blue dot, right? 2, 3, yeah, 2, 3, and then there's 4, so 1, 2, 3, 4. It nicely fits in this upper half of this 5 by 5 square. Yeah, this is n equal 5 case. Yeah, k equal 2. And then when you look at red dot, you go northwest. Yeah, and then this one is the first red dot sequence. So you hit this one, the first column next to this bar. Yeah, there are 2. Right? And then there's 3 dot. This one hits this box. Yeah.
So in this case, which will actually Grassmannian? In this example.
In this what? Example?
In this example. Are you considering 2-dimensional space or 3-dimensional space?
So when I say n equal 5, k equal 2, this is 3-dimensional isotropic subspaces in C10. Yeah. Okay. And then another example, 3, 5, 4 bar, 1 bar, 2. Yeah. So you have black box 4, 1, and then you have 2 red dots. Yeah, and 1 blue dot, right? Blue dot first because it's 2. Yeah, and then 3 dots, red dots, and then 5 red dots. Yeah, and then you go northwest and you hit this box, and then this one hit this box. Yeah, and then 3 box, and the partition becomes 6, 3, 2. Yeah? So existence of this red boxes in this picture is the difficult part for the isotropic Grassmannians. It didn't exist for Lagrangian case, like maximum case, or it didn't exist for type A case. Yeah? Okay, and isotropic Grassmannian now. Yeah. So now the IGNK means it's a n minus k dimensional isotropic subspaces in Cn. Yeah. And right. So from this combinatorial objects, k-strict partitions or k-Grassmannian permutation, it indexes Schubert classes of this isotropic Grassmannian. Yeah. So, so now you represent. Now you're looking at this cohomology ring as the module generated by Schubert classes. Yeah? And now you want to think of this as a ring. Yeah? And then what's the generator? So you want to have a certain polynomial expression of this ring as a polynomial ring. Yeah? And then there is another proposition. Basically this cohomology ring is isomorphic to a ring generated by certain generators, k theta 1. Yeah? And this k theta 1, it's a subring of the whole big ring given the cohomology of flag variety. So it's given by x, z, t parameters. Yeah? And then this theta polynomial is defined by this generating function. Yeah? And when you were looking at the polynomial ring for the flag variety, you didn't have this part, z parameters. The q is defined by this one, and then you just add this extra part, and then you have this theta polynomial. Okay, so now you have a generator of the cohomology ring of isotropic Grassmannian, and now the question is, how can you describe the Schubert polynomial corresponding to the Schubert class in the isotropic Grassmannian in terms of those generators. Yeah? And then actually writing this double Schubert polynomial in terms of these, it's a little complicated. So we allow a little bit more flexibility of this theta polynomial. Yeah, so shifted theta polynomial. So now you add t parameters. Those t parameters corresponds to the equivariant parameter. So, so this part, yeah, the first two components are coming from the generator in the last slide, and then you just multiply this. So it's going to be equivariantly shifted theta polynomial. So number of t parameters involved in this theta is indexed by L, and so you also introduce this minus L, and then you divide by this 1 minus TIU. Yeah? Anyway, both number of T's involved are specified by this L. Yeah? And Giambelli problem is basically find a closed formula of this double Schubert polynomial in terms of those theta polynomials. Okay? And for those people who know a little bit about Giambelli problem already, so this theta polynomial correspond to special Schubert class, yeah? Associated one-node partition. So basically, if you take the non-equivariant limit, the formula we are trying to find gives you a formula of a general Schubert class in terms of special Schubert classes. And you can also interpret these thetas in terms of Chern class of tautological bundles associated with the Grassmannian. So that part I'm going to skip. Yeah, but there's a lot of geometric interpretation of what those parameters are. Okay, and to describe, this double Schubert polynomial, we need some algebraic operation. Yeah, the multiplication, addition, that's not enough to describe things. Like in the type A case, the Giambelli formula gives you a determinant formula. Yeah, so determinant is certain operation. Algebraic operation that is, we can think of it as a closed formula if it's written in terms of determinants. But that is what happened in type A. And in type C, instead of determinant, we are supposed to do Pfaffian. We learn it from the early works. Yeah? So what's the Pfaffian? So Pfaffian is usually defined for skew-symmetric matrices, but there's some generalized version of Pfaffian called multi-Schur-Pfaffian. So this is something Schur invented. So this is notation. So we use this formal parameter C's. It's a sequence of parameters. Yeah? And then if you insert one parameter, it's just that CM1. Yeah? And then if you input two sequence here, yeah, indexed by M1 and M2, then it sort of alternates, but then you multiply 2 after the first term. Yeah, and then the degree, this M1, M2, it's going to be shifted by 1 each. Yeah, the second index M2, you subtract 1, and then you add 1. So generally, this lower index gives you the degree of the parameter, and the degree will be preserved. Yeah, degree is M1 plus M2, and then if you proceed ahead, still the degree is M1 plus M2. Okay, and then this goes infinite, right? So it's actually this two-term Pfaffian is infinite power series, but then later we're gonna assume that if this m is negative, then it's 0. Yeah. So in the end, we're going to make a polynomial. Yeah? So the question is, what happens for if you insert 3 or more terms? Yeah. And then it's different in odd case and in even case. The odd case you can define it this way inductively, and also for even case it's defined this way inductively. And this, if you look at the formula for even case. And this actually gives you the usual Pfaffian of the skew-symmetric matrix, whose entries are given by those two-term Pfaffian, described this way. Yeah?
Is it some kind of Binet-Cauchy formula? Or?
Binet-Cauchy formula.
Like decomposition of, does correspond to anything, to any decomposition of the determinant? Like
so I think this is actually the analog of a cofactor expansion, the row.
Okay.
Yeah. Like the inductive way of defining the determinant.
Yeah.
Yeah? So this is the inductive way of defining Pfaffian. Yeah? So the good thing is, it's worth noting that this is just a linear combination of those monomials. Yeah? And a priori it's infinite series, but after you set Cm equals 0 for m less than 0, then it just becomes polynomial. Yeah? And using this, we can write the formula. Yeah, and before our work, there is a Kazarian's work and Ikeda's work. This is for k equals 0, which is Lagrangian Grassmannian. So you're collecting Lagrangian subspaces in symplectic vector space. Yeah, the corresponding Schubert polynomial, it's given by Pfaffian, and those Q's are we set k equals 0. Right? So it's Q. They use notation Q, but now I use theta because it's going to generalize to isotropic Grassmannian case, a more general case. But this is like Jacobi-Trudi formula for type C. Yeah? And general isotropic case is our main result. So now we need a little bit of a notation here. Right? So this d lambda is the pair of index I and j. I and j is from 1 to m. Yeah? And I think I forgot to put lambda. So lambda is a strict partition, and lambda 1 through lambda m is each number in this partition. And there's a corresponding characteristic index, and then this inequality satisfied. You look at those pairs. Yeah? And then for each subset of these pairs, you write this shifting index. Yeah. So if this S, if S is in the first slot, then you increase, and then if S is in the second slot, then it decreases. Yeah, so basically that's what happens, and those shifting operations of the index. So in the previous Lagrangian case, you just put partition as the degree of the lower index, lambda 1 through lambda m. Yeah, and then upper index you put chi 1 through chi m. Yeah? And then in the general Grassmannian case, you have to sum over all subsets of this d lambda. Yeah? And then again it becomes Pfaffian, but each entries are all shifted by this shifting index. Yeah? So it's actually hard to convince this formula right now, but let me. Okay, I had so the way we proved this conjecture was there's this left divided difference operator that sort of connects all the double Schubert polynomials, and there is some definition. There is a definition of left divided difference operators, but what's important is this compatibility, right? So you start with some double Schubert polynomial, and then you apply some left divided difference operator indexed by those S0, S1, S2, S3, those transpositions. Yeah? And if so double Schubert polynomial is indexed by Y group elements, and if this Si decrease the length, then it gives you the next lower double Schubert polynomial. Yeah? So in this way, once you have a good formula of the double Schubert polynomial indexed by some Y group element, then you can just calculate all other by applying divided difference operators. But then, so we are using this compatibility condition to calculate the formula for double Schubert polynomial for isotropic Grassmannian. But the key fact is we know that the formula for the longest elements of the wire group. Yeah. So you start with this Pfaffian expression, and then if you know how to apply double divided difference operator nicely, like keeping this Pfaffian form, and then you can just get all the Pfaffian expression of other double Schubert polynomials. Yeah. So now it's described in terms of those theta polynomials. So what you need is Leibniz rule, because it's a polynomial of those monomials, and then also how this divided difference operator acts on this theta polynomial. And then actually it's very compatible, right? So you can handle this as certain rules to compute. And then I can give you the example. You start with some Pfaffian formula, and then this is polynomial, linear combination of these monomials, but then this lower index going to be shifted, right? But this shifting is controlled very well, so this compatibility condition, this application of divided difference operators for the monomial, it just goes through this Pfaffian, and so if you look at I minus 1, okay, so, right, so, yeah, so 0, you apply partial 0, and 0 becomes minus 1 from this first formula. And then now you have 1 and minus 1, and so you apply this formula. So upper index becomes 0 and minus, so you subtract 1 each, right? Upper index, subtract 1. And then lower index, there are two terms. You subtract 1 from one index, and then next term, subtract 1 from another index. Yeah? So 4-2 becomes 3-2 and 4-1. And this is the source where the Pfaffian becomes two Pfaffians. Yeah? And this was kind of a new observation when we were making this Giambelli formula. Yeah? Okay, thank you very much.